Hello, everyone. Can you guys hear me?
Yeah.
Okay, sounds good. Okay, so this is the IEEE Cookies and Cram CSI 2110 review session. I'm going to be covering majority of the concepts covered in CSI 2110. So here's just an overview of the topics that I plan on covering. For a majority of the questions, I've picked out some exam questions. Or a majority of the topics I've picked out some exam questions. So yeah, that's basically it. So let's just get started. So the first topic that was covered was time complexity. And there are the three time complexities, which is the big O notation, big omega notation, and big theta notation. So in terms of like actual functions, the big O notation acts as the upper bound, the big omega notation acts as the lower bound, and big theta acts as the tight bound. So what is that clear? Generally, big O notation is used to describe the worst case, and big omega is generally described to use the best case. So generally on the exam, you'd only see big O or big theta. You rarely see big omega. However, it's always important to just keep in mind that each symbol refers to a different thing. Sorry. So I have picked out a following multiple choice exam question. So given the following snippet of code, we are asked to find the big theta notation. So I guess I'll just walk through it. So big theta notation refers to both big O notation as well as big theta notation. So first we need to figure out what the big O notation is. So in the first line, it take only O of 1 since it's initialization. And then in the following line, it take O of n because we'd be iterating through a loop for n over 2 times. However, this would simplify to O of n. And then in the next line, we'd be iterating for log of n because we'd be iterating from 2 to n, but since we'd be incrementing by j times 2, we'd be incrementing exponentially. So because of that, it'd iterate for a log number of times. And then finally, within all the for loops, we have k is equal to k plus 2. It's not dependent on n, therefore it'll take constant time. And then finally, outside of all the for loops, we have the operation return k, which also takes constant time. So using all this information, we can derive that the big O is O of n log n. So now that we know the big n log n, we'd choose between the options of B and E, because the big theta notation would require us to have a big O as well as a big O and big omega in order to have a big theta. So because of this, it's either between B or E. B or E. So because of that, we now need to find the big theta notation. So in terms of the worst, or in terms of the best case, we can only alter the value of n. So in terms of what we can actually change, there isn't much, as there isn't any if statements in order to actually change the time complexity. So again, it'll share all the same time complexities as the lines I've written out. So it will also have a big theta of n log n. So since we know that it shares both the same time complexity for big O and big theta, we can now safely say that it has a big theta of n log n. So it's answer B. And so are there any questions regarding this example? Take a seat anyway, it's fine. Okay, I'll be moving on. So this is another time complexity question. It's a little bit longer because this is not actually multiple choice. But it's asking us to find the big O of the following function. Fn is equal to n squared plus log 2n to the 4 and prove that it's equal to O of n squared. So going back to the definition of big O, it's defined as f of n is less than or greater than c times g of n, where in this case, we need to prove that g of n is n squared and f of n is given. And we need to find some value of n0 such that it is greater than, or equal to c times gn for all values. So using that, first begin the proof by saying f of n is equal to n squared plus log 2 of n to the 4. Eventually, we're going to have to use an inequality sign in order to show, or in order to convert some of the terms. And I'd begin by converting n squared, or I begin by removing the power in n to the 4 and using log rules. And on the right side, we have an O of n squared. So this is just to make sure that we're on the right track. Okay, so we need to somehow prove that 4 times log 2 of n is less than n squared, such that we can make all the terms n squared. So how can we prove that? Well, we're actually given those because we were forced to memorize. Sorry, scribbling. But we're actually forced to memorize these following values and their inequality. So I'll show the slides afterwards. Yeah. So since we know that O of log n is less than n squared, so then we can safely assume that this is less than 4 times n squared, 4 times n squared plus n squared. Okay, so from there, we just combine all the terms, and then we can see that the constant value is 5, and that the gn is equal to n squared. And if you want, you can write a therefore statement, but I guess this is a solid enough proof. So are there any questions? Oh, my bad. What is a binary tree? I'll get to that in a minute. And oh no. Okay. Are you guys okay with seeing my desktop, by the way? It's very messy, I know. But oh, they can't see it?
Yeah, it's only sharing that.
Oh, okay, cool. Are you okay? Sure. Okay, then yeah, that's fine. So are there any questions just about the proof? Oh yeah, I forgot to mention NO was less than or equal to 1 because given again these values that we needed to memorize, they apply for all n0 greater than or equal to 1. Okay, I'm assuming there are no more questions. Okay, so moving on, we're gonna be looking at lists. So there are a lot of lists covered. There was a stack, there was a queue, there was a DQ, there were a lot of them. But again, I'll just be reviewing them very briefly. Again, stacks, just like any other stack in real life. When you push an object, it goes to the top of the stack, and then when you pop it, you take the top element. Q, you pushed it into the queue, and then you'll take the first element that was pushed in. DQ can be performed on either, can perform an add or remove operation on either side. So now we have an exam question regarding queues, and I'm pretty sure this showed up on our midterm. So consider the queue implemented by the circular array with the following contents given. So we have the front index being equal to 0 and the rear being equal to 4. So show the data structure after the following operations executed in the given order. So DQ, InQ, DQ, and InQ. So an important point to note is that this is a circular array. So any operations we do like InQ or DQ will change where the front and the rear are located. So first, I just begin by writing out all the initial values and then going about each operation. So first, we have the DQ. We know that the front is located at 0, so we simply remove it and move the front to 1. Next, we have InQ. So we place the value of B at the rear, since it's a queue. So that'd be at value 4. And we'd move the rear. Oh, but again, it's a circular array. I almost forgot. So we want to make sure that we move to the value of 0 because there's nothing here. So we have value 0. DQ. Again, we take the front element, which is 1, and we make sure to move the front. And finally, we have NQ, A. So when we InQ something, again, put in the rear. Rear is located at 0. And then we simply input the value A. And we shift the value of the rear. And this should be the final answer. So let's just check to make sure. 2, 1, all the values are shifted. So does that make sense? Okay. Are there any questions regarding queues, stacks, or DQs? Okay, sounds good. So next were the more complicated lists like array lists, positional lists, and sequences. Array lists work exactly like an array, except that when they reach full capacity, we have to extend them and shift all the contents from the original array list to a new array list. And in a positional list, it's a linked list. It works exactly like we expect a linked list to. Positional list right here. It stores a value as well as its previous and the value in front of it, or the node in front of it, my bad. So you can see here, it stores the value or the node, the previous node, as well as the next node, as well as the value, in which case it's a picture. There is no notion of rank in a linked list. So you wouldn't be able to index a linked list without iterating through every single value, unless we were referring to the header or trailer. So we need to iterate through every value because, again, there's no notion of rank. So we have to go through every single value before we actually find the value that we're interested in. And finally, sequences, just a very broad term to refer to either a combination of a positional and array list. It holds both a positional index and works similarly to an array. And it's just generally a very broad term. It's used later in later parts like bucket sort to indicate like lists. Questions? So here are some of the time complexities. They're pretty common, they're pretty common for multiple choice, but I didn't pick out one. So I wouldn't recommend memorizing these. I would just honestly just remember the ADTs and just try to derive the time complexity on the spot. I don't think memorizing these would do much good, but they're just here just in case you want to. And then finally, the last list type is a priority queue. The priority queue is holds comparable keys to each of the list items. So there are multiple implementations of a priority queue. You can use an unsorted sequence. Sorry, unsorted sequence, sorted sequence, as well as a heap, which is like pseudo sorted. So they change the time complexities pretty drastically, depending on which implementation you use. But generally, when you are given the question, you'll be told which implementation is being given to you. And usually these are used in order to like return values at constant time, or at least with the sorted sequence. Are there any questions regarding priority queues or the more complex list ADTs? Okay. All right. So now we're going to be moving on to trees. So here are all the non-search trees, or all the terms used to describe them. So a full binary tree refers to a binary tree with only 0 or 2 children. So here we can see only has 2 children or 0 at leaves. A complete binary tree refers to one that's filled from left to right and up to down. So it's filled in order, reading from left to right and up to down. The degenerate tree, which is just a linked list. One of the properties is that the number of nodes is equal to height plus 1. That was useful on the midterm. So a perfect binary tree has a height equal to, or has number of nodes equal to 2 times the height plus 1, or 2 to the power of the height plus 1. And for this one, as well as the full binary tree, the property applies that the number of external nodes is equal to the number of internal nodes plus 1. And finally, for the balanced tree, we must ensure that all the branches do not differ by a height of more than 1. This is mainly useful for ABL trees, but it can also help for binary search trees, increasing their time complexity. Are there any questions regarding these terms? I remember someone asking, what is a binary tree? It's a tree with 0, 1, or 2 children. Okay, I'm gonna take silence as a yes. I mean, as nothing. Okay, so for pre, post, and in order traversals, we're interested in visiting each of the nodes in a very specific order. There are 2 types of problems you can be given for this. The first being you're given 2 of the orders and you're forced to make the tree from scratch. Or you can have the second problem in which you're given the tree and you're asked to derive one of the orders. So generally, when they ask for the orders, I highly recommend using Euler's method. So what Euler's method is basically you start from the top of the tree and you slowly circle around the tree. And every single time you touch the sides of the node, depending on which order you're interested in. So let's say, for example, I was asked to find pre-order. I would circle around the tree. And in the order I touch the nodes, in the order I touch the left of the nodes, I'd write them down. So I see A, B, D, E, G, go around, F, H, I. Oh, I missed C. Oops. C comes after D. A, B, D, C, E, G, F, H, I. Yeah. And that matches the pre-order. So that's how you derive the pre-orders pretty quickly. You can also do it using the parents, or I wrote it here already. The parent left right iteration and doing it recursively. But again, I highly recommend, since this is a pencil and paper exam, that you use Euler's method. Is a lot faster. Yeah. But these orders and remembering them are required when you need to construct the tree again, using only 2 of these orders. And generally, when using Euler's method, if you are asked to find in order, you'd look at the bottom of the node. And if you're asked to find post order, you'd look at the right of the node. And the left one. Oh, chat. Yeah, I forgot to see. We share these and the slides at the end. I can try my best. But if there are any questions regarding Euler's method, I just recommend searching it. I'm definitely sharing the slides at the end though. And there'll also be the recording. Are there any questions regarding Euler's method or any of the pre-orders or any of the orders? No. Okay. So here we're asked to find each of the pre, post, and in order. So again, using Euler's method. Quickly circle around the tree. And then I'd see that every single time I touch the left. So 8, 5, 9, 7, 1, 12, 2, 4, 11, 3. Yeah. Always make sure that when doing these orders, that the root is located at the beginning, end, or middle, depending on which order you're doing. So for pre, it'll be at the front, post would be at the end, in order somewhere in the middle. So for post, you get 9, then 1, then 2, then 12, then 7, then 5, then 3, then 11, then 4, then 8. Again, root located at the end. Then finally, for in order, first it'd be 9, then 5, then 1, then 7, then 2, then 12, then 8, root located in the middle, then 4, then 3, then 11. Yeah.
I don't know if you said this, but is there any point worrying about an Euler tour?
Sorry?
I don't know if you said this, but is there any point worrying about an Euler tour?
Euler tool? Oh, I just do it because it's a lot faster.
Okay.
You can worry about the or not worry, but like You can also do the other method. I just think it's a lot faster.
They're gonna ask us questions directly about it.
Yeah, that's true. I don't know, but these are just some of the ones I found on the exam. Yeah. Also, yeah, we'll be doing the hash table. But we'll be only going over problems that I found in the slides. I don't think I pulled any from the exam. Okay. Are there any questions regarding pre-post or in order traversals? Yes, there's a lot on graphs. In addition to trees, I'll be covering a lot of the graph traversals. So like breadth search, graph traversal. I'm just starting from the beginning of the semester, that's why. Okay, are there any more questions just about anything? Okay, moving on to binary search trees. So binary search trees hold no search or binary trees in which the key of the left child is always less than the parent, which is always less than the key of the right child. So we can see this here in the first subtree, in which 2 is less than 6 and 6 is less than 9. And here are all the time complexities. Again, it matters if it's balanced because being able to, or the worst case in which it would be balanced would always be log n. Because you'd always be iterating down by one level each time you perform a search. And since the height is equal to h+1 for or roughly for a binary search tree, then we know that the search time would be logarithmic. So are there any questions regarding binary search trees?
Did you just say greater, or it says right child less than, or always less than?
It's just a one big inequality. Yeah. Okay, moving on, binary search tree. So which of the following is a binary search tree? We need to make sure that the property holds that the key of the left child and is less than the key of the parent, which is less than the key of the right child. So we need to begin by checking each of the trees. So first begin by examining the lower level and ensuring that each of the keys follow the property of a binary search tree. So we know that 2 is less than 3, 3 is less than 4. And then here, perform another check on the subtree, we can see that 3 is less than 5 and 5 is less than 7. So we know that 1 is a good subtree. So moving on, we can see that 2 is less than 3. There's no node here, so we wouldn't need to check it. So we only need to check that 2 is less than 3. Here we can see 3 is less than 5. 5 or 5 is less than 7. And then finally 6 is less than 3. Or 6 is less than 7. So we know that 2 is also a good binary search. So in 3, we can see that again, all the values are less than one another in the upper level. So again, this is also a binary search tree. We can see that 3 is less than 4, 4 is less than 5, and 6 is greater than 5, 7 greater than 6. So 4 is also a valid subtree, binary search tree. And then you can see, check. You can see that 3 is less than 4 and 4 is less than 6. We can see that 4 is less than 6. 4 is less than 5. And 5 is less than 7. But we need to make sure that all the parents' keys in the left subtree, or all the children keys in the left subtree are less than the parent key. So we can see that 6 is greater than 5. So because of that, we know that's not a valid. So we know the answer is A. Are there any questions regarding binary search tree and its properties? Okay, well. So for insertion, we want to go through each of the levels, checking the parent key and determining whether or not the node we're inserting is less than or greater than the value, less than the value than we're inserting. So if we wanted to insert 78, it'd be less than 88. So we go left, and greater than 65, so we go right. And then we'd slowly progress down until we hit the bottom, and then we just add the node there. Are there any questions regarding insertion? I know. But the thing is, I only have 2 ports. I do, but it's only 2 ports. Yeah, I only have 2 ports because I need the adapter and. Okay, so moving on, we're going to talk about the removal from a binary search tree. So there are 3 different cases we can encounter when removing from a binary search tree. One is in which there are only leaf nodes attached to the node we want to remove, in which case we simply remove the node from the binary search tree since all these other nodes are null. The second case in which we want to remove from a binary search tree is in which we have one subbranch as well as one with null nodes. And then we begin by removing the node and then reattaching the subbranch to where the 4 was originally. And then finally, we have the third case in which it's attached to 2 subbranches. So let's say we want to remove 3. So first we begin by removing the node, but then we'd have to find a replacement. So there are 2 options. We can either go to the left and find the greatest value in the left subtree, or go to the right and find the smallest value in the right subtree. So this ensures that we find the closest replacement for 3. And in this case, we choose the value of 5. And we just put it in the original place of 3. And yeah, that's the removal. Are there any questions regarding any of the cases for removal from a binary search tree? Okay, moving on. So for heaps, we need to ensure that or at least for a min heap, that the key of a child is always greater than the key of the parent. And for a max heap, that the key of the parent is always greater than the key of the child. Here are all the time complexities. If you're interested. And yeah, are there a heap is a complete binary search tree. So whenever we insert, we are always inserting from the bottom left. So if we were to insert another node, we'd insert it here. And with removal, we generally only remove the root node because we want to usually perform heap sort. So when we remove the root node, we'd take the child node or the rightmost bottom level child node and place it in the root and then perform a down heap operation until the heap satisfied the property of min heap or max heap, depending on which one you have. Okay, so again, if you want to insert a node, we want to if we wanted to insert the value, for example, Z. This is a max heap. So again, if we want to insert it, we'd always place it at the bottom and then slowly perform up heap operations. So we'd see here that I'm assuming this is a no, so we'd swap it. And then again, we want to perform an up heap operation, this time on the bigger sub branch. And then finally, we want to perform it on this sub branch. So again, we see that Z is the greatest alphanumeric value. So we do want to swap it with S. Sorry, it's messy. Okay, are there any questions regarding insertion? Okay, so here's an example. Actually, I'll just skip it. We already went over one. But yeah, just in case you're interested. Yeah, okay, so removal of a node. Let's say we want to remove the min because we have min heap. We want to remove 3. So we'd first remove the value 3 and return it. And then we take the rightmost bottom level child, in which case it's 20. We'd move it all the way to the top and then progressively down heap. So if we perform 20, if we had 20 originally here, well, work on the original. So if we had 20, so since this is a min heap, we want to take the lowest value child. So we swap 4 and 20. And then we perform another down heap operation. We have the values 21 and 10. Since it's a min heap, we swap 20 and 10. Again, min heap, looking for a minimum value. So we swap 13 and 20. And this gives us the answer. Are there any questions regarding heaps? Insertion, deletion, properties? Depending on which operation you're interested in, for a heap, it'll take log n on all operations. Okay, but anyways, the general gist of it is that there's a trade-off between insertion as well as removal of min, or finding the min key as well as removing min. So generally speaking, a priority queue with the sorted sequence is faster for okay, here we go. So it's generally faster and with the sorted sequence at finding them in and removing them in. But in terms of having a sorted sequence and inserting a value, it takes n time versus being able to insert a value ad log. So in some cases they're faster, or in some cases, a priority queue with the sorted sequence is faster. In some cases, a heap is faster. So moving on, I'm gonna have a question regarding heaps. So considering the max heap, given using the following array to store its elements, which of the following is the array after one remove max operation? So first we need to perform a heap construction. So begin by reading from left to right of the array and building a binary search tree. Since it said it was a max heap, it was already in order. We don't need to perform any heap operations. So if we wanted to perform a remove max, we first remove the value of 10, and then take the bottom rightmost child, which is 2, replace it with the value of 10, remove the value of 2, and then perform down heap until the heap is a max heap. So since it's a max heap, we always want to look for the maximum value. So in this case, it'd be 5. So 5 and 2. Next, we'd want to perform a down heap operation on this subtree. So we look for the maximum value, which is 4, and swap over 2. And this would be the max heap that's constructed afterwards. So the array reading from left to right up to down, 4, 3, 1, 2, and then since it's an array, the node would still be there. But if we were using a tree, the node wouldn't be there. So 4, 3, 1, 2, 5, or 4, 3, 1, 2. So that's values. Are there any questions regarding how removal of max would come? Okay, so this wasn't covered in any of the assignments, but it was done in the lecture slides. It's the general tree conversion to a binary tree conversion. So the general rule when converting a general tree into a binary tree is that you want to copy the root node as well as the leftmost children. And from there, we'd want to iterate through every single node. And once we iterate through every single node in pre-order, we want to check to see if it has a right sibling. If it does, we want to draw it as a right child. So again, we'd want to iterate through everything in pre-order. So first we go through A and B, then E. Do you guys want me to go through this example? Okay, sure. Okay, so first we go through the value of A. We check to see if it has a left child. It does. We start with A. We see that it has a left child. So we copy the left child. It doesn't have a right sibling. So we leave its right child alone for now. Next, we move on to B. We check to see if it has a left child. It does. We check to see if it has a right sibling. It does. We copy it. Then we move on to E. We check to see if it has a left child. It doesn't. We check to see if it has a right sibling or a direct right sibling. My bad. It doesn't. So we move on. Then we go to C. Does C have a left child? It does. Does C have a right sibling? It does. Then we go on to F. It has none. We see G has none. Oh, wait, my bad. F, it does have one. It has a right child because it has a direct right sibling. And so does H. Or so does G, my bad. And then we move on to the value of D. C. Okay, so from D, we can see it has a left child, which is I. And then does not have a right sibling. Then we check node I. Does not have a left child, but it does have a right sibling. Then we check the node J. Then J has a left child. Does not have a right sibling. Then we check the value K. The value K doesn't have a left child or a right sibling. And that'd be all the values. So yeah, that's how to convert general tree into a binary tree. Are there any questions regarding the procedure? Okay, moving on. We have the AVL tree. So the property of the AVL tree is that it's just a balance, it's a self-balancing search tree. So we'd always want to ensure that the branches never differ by a height of 1. So we can see in this example that none of the branches ever differ by a height of 1 or more than 1. So it can the left child can be have a height difference of 1. The right child can have a height difference of 1. All nodes would need to satisfy this property. So. And these are all the time complexities. It's for AVL trees is log n of everything, but except for space complexity. Are there any questions regarding the properties of AVL trees? Okay. So insertion is the exact same in an AVL tree as it is in a binary tree, except that it needs to self-balance afterwards. So in this example, we want to insert the value of 54. So we'd simply go about inserting it like we would a binary search tree. So we see it's greater than 44, but less than 50, or less than 78 and greater than 50 and less than 62. So then we just insert the node there. But afterwards, we need to check to ensure that all the branches are balanced. So we'd begin by checking the smallest subtree, and in which case we can see that, sorry, it's messy, but we can see that the difference in height is 2 to 1. So it'll only be a difference of 1. Then we check the subtree with a height of +1. We'd see that the depth of the left branch would be 2. And the depth of the right branch would be 3. 1, 2, 3. Or no, would be 2. excluding the null nodes. So we'd have a depth of 1, depth of 2. So the difference would be 1. It still satisfies the property. Then we'd increase the height by 1. We'd check the height of the left subbranch. We'd see that there are 3 nodes versus the right subbranch, which is only 1 node. So there we can see that there's some imbalance and we need to begin rebalancing. So to rebalance, you'd want to start from the node which is causing the imbalance, in which case, or the parent node which was causing the imbalance, in which case it was 78. And slowly work down the height in which the height, slowly work down the branch which has the greater height. And you'd want to label the 3 nodes going down with Z, Y, and X. So in this case, they're already labeled. And from there, you'd want to, or in there, you'd always have 4 sub-branches. So you'd want to circle each of them going from left to right, labeling them T0, T1, T2, and T3. And then you'd want to choose the median of the values of X, Y, and Z as the new parent of that subtree. So in this case, it was X because 50 would be the minimum, 62 would be the median, and 78 would be the maximum. So we'd want 62 to be the new parent of that subtree. So we place X at the top. And then we place the minimum in the left subtree and the maximum in the right subtree. From there, we place all the sub branches that we circled originally in order from left to right. So T0, T1, T2, and T3 as the children of the minimums and maximums. Does the insertion make sense? Okay, so moving on, we'd want to worry about deletion of a node. So again, it's the exact same as a binary search tree, except that we need to ensure balance afterwards. So if you want to delete a node, in this case, don't believe it. Oh, okay. We want to remove the value of 32. Okay, so in the original subtree, there was a value of 32. So let's say we wanted to remove the value of 32. So this will cause imbalance in the parent node. You'd begin by checking the smallest subtree, but in this case, it's a null node. So we'd check the entire tree because this would be the root node. So we'd want to ensure that the entire subtree is checked, or the entire tree is checked for balance. So we choose the deepest branch in the right subtree as well as the deepest branch in the left subtree and check further heights. So this one will only go down 1 node, and we can clearly see that the height difference is greater than 1. So we know that there's imbalance. So we'd begin by, again, labeling the values, starting from labeling the values going down the deepest branch with ZYX. It's already labeled. And then from there, we choose the median, in which case it's 62. 62. We'd replace it with the root node and then place the minimum, the left subtree, and the maximum in the right subtree. Then from there, we need to circle the T0, T1, and T2. So in this case, this would be T0, T1, T2, T3. And then you'd place them as sub branches of the minimums and maximums. Are there any questions regarding deletion? Oh, chat. X is the pair node that causes the imbalance, then go down. Oh, how do we pick X, Y, and Z? We'd want to go down the branch of the greatest, or the branch of the greater depth that's causing the imbalance. So in this case, we were working with the entire tree. So we were checking the left subbranch and the right subbranch. So we'd want to check the heights between the two. So we'd go down the left subbranch and see that it's only a height of 1. And we go down the right subbranch and see that it's a height of 3, which causes imbalance. So we choose the subbranch with the higher height, which is height 3. And then choose the parent node as well as the 2 nodes leading down the branch with the greater height. So in this case, it'd be ZYX for, because these are the values that are causing imbalance. You could have also chosen, what was it? Like 54 or 48, because they're also of the same height. It's just that in this example, 78 was chosen, so that's why the ZYX value, that ZYX value is chosen. You could choose other values though. Does that answer the question? Okay. So moving on, we have the 2-4 tree. So with the 2-4 tree, we would always want to have at least 2 to 4 children, as well as each node containing at least 1 to 3 values. In the case that there's less than 1 value, we'd refer to it as underflow. And in the case that there's more than 3 values, we'd refer to it as overflow. Again, for all the insertion, deletion, and search, they're all of log n time. And with the values of the nodes, we think of them as intervals. So if we were looking at this node 258, we'd assume that all the left child of 258 has only values which are less than 2. So this holds true because the only value there is 1. And then in the case, if we were looking at the middle child, the 3-4 middle child, we notice that all the values are in between 2 and 5. For the 7 child, we notice that all the values are in between 5 and 8. And the rightmost child has values greater than 8. So we want to ensure that this property holds like all the time. And we do that by checking for overflow and underflow when performing insertion and deletion. Is there more than one? Yes. Yeah, there is. Because when there's in a case of overflow, when there is a case of overflow, I'll get to that in a minute, but okay, so when overflow occurs, you can choose between the two middle children to move them up. And you'd always shift the left or rightmost child over to the sibling node. So you'd end up with a different tree if you chose a different child. Because let's say, for example, if I wanted a different tree from the one that we have here, we can see that we chose the value 32 to move up. So instead, I can choose the value of 30 to move up. And then I'd move 27 over to the sibling node. But again, it would cause overflow. So we need to shift everything up by one. This is a special case in which the parent node has overflow. So we'd shift one of the children up to be the new parent of the subtree. So you can choose between 24 or 15, it doesn't matter. Don't know how to do this nicely. And that'd be your new subtree. Or that'd be your new tree. Oh, yes, they're all right though. As long as the property holds that each interval and their children satisfy are less than or greater than whatever specified in the interval, then it should be fine. So is that all right? Did I answer your question? Okay. So with insertion, there's only really one way of, or like not one way of going about it, but there aren't multiple cases. But okay, so first, are there any questions regarding insertion and overflow? But with deletion, there are multiple cases because it depends on whether or not the sibling has one value or more than one value. The reason is because we can steal from the sibling or not steal from the sibling. So in the first case, we can see that there's underflow when we remove, I don't even know what the value was. Okay, but we removed value and now there was underflow. So then we'd want to, in the case one, we want to steal from the parent and shift the middle child into the parent, or not into the parent. We want to steal from the parent as well as the sibling and place them both in the empty node to prevent underflow. And yeah, we delete the middle child. But in the second case, we have two children. So in that case, we'd want to shift one of the values from the middle up, and we want to shift one of the values from the parent to the right. You choose the, you choose the values based on which child you're working with. So if we were working with the leftmost child, then we choose the value 4 when shifting one parent over. And in the case of choosing a sibling value, we want to choose the rightmost one because we're shifting to the right. My bad. I didn't mean to draw that. Okay. These are the two cases for deletion. Are there any questions regarding deletion? Kind of wasn't clear. Question. Okay. I'll keep moving. So that's it for trees. And we're going to be moving on to sorting. So first we have the simple sorts like insertion sort and selection sort. They take O of n squared time. For selection sort, you're repeatedly looking for minimums and placing them at the beginning of the array. For insertion sort, you're creating a subarray and then slowly adding elements in their position one at a time. Do you guys want me to go over an example? Okay. So then moving on, I'll just skip the question. We have merge sort. So merge sort, given an array, we want to break it down into a subarrays of one, and then slowly combine the array, ensuring that each subarray is sorted. So in this example, we have 750, 70, 50, 30, 10, 20, 40, and 60. So we want to break it into groups of two. So it's pretty, but again, we break it down into subgroups of two until we reach subarrays of one. In this case, we have an odd number, so we'd ensure that the pair at the end only gets one. So when we combine the subarrays, we got to make sure that they're in order when they're sorted, or their order when they're combined or merged. So 50 would go before 70, 10 would go before 30, 20 would go before 40, and so on. And then we'd repeat this process by merging again and ensuring that the subarray with greater values appears after the subarray with lower values. So 10 and 30 would appear before 50, 70. But this doesn't guarantee that you wouldn't have to mix the subarrays, because we know that the value 10 and 50 are, or we know that the values following 10 and 50 are greater than what is at the front, but it doesn't necessarily guarantee that the value following 10 is 30, for example. We could have had 90. And in that case, we'd need to sort it like so. So it's not guaranteed that the subarrays will be connected. Does that make sense? And then, oh my bad. Finally, you combine all the subarrays at the very end. Again, they're not in order. It's not guaranteed that they'd be in order. You'd only be comparing the frontmost values and then slowly building them onto one another based on the subarray and merging them. Are there any questions regarding merge sort? Okay. So
Actually, yes, what's the worst time complexity?
and sort. Wait.
Did you say? You said
Wait.
for which-
Not quite sure. I didn't specify. My guess would be n squared, but I'll search it up afterwards. But sorry. Yeah. Okay, so I'll just work on this example really quick. This is just an in place.
It's n log n.
What is it?
It's n log n.
Thank you. Okay. Yeah. So this in place implementation. We first want to break this array into subarrays of length 1. So first it's sure that each of them are broken down into partitions of 2. And we'd be working from left to right. So in an input implementation, we want to ensure that the first subarray is in order, then second, third, fourth, and then slowly combine them after each line. So the first step, we want to combine the subarrays 30 and 10, and everything else would remain the same. And then we'd want to combine the subarrays 50 and 20. Sure that they're in order. 15 and 7, 2 and 12. Next, we want to combine the subarrays 10 and 30 and 20 and 50.
When you do the 2050 and the 15 and 7, you switch those both in the same line.
Hmm?
You switch.
Oh, my bad. Yeah. No, you're not supposed to switch them. So next, mention 20, 715. We'd want to organize this subarray. Next, we'd already see that this subarray is organized, but we need to waste one iteration checking it, or merging them. And then next we work on subarrays of length 4. So we'd want to combine 10 and 30 and 20 and 50. So visually, we can see that 20 is greater than 10. But afterwards, there's no guarantee that whatever is following, we need to check, whatever's following would be greater as well. So we can't necessarily guarantee that 50 would be greater, but in this case it is. So we do 20. What I'm trying to say is we also need to check it. From there, we combine the other two subarrays. So in this case, we'd be combining 7 and 15 and 2 and 12. So we'd see that 2 is the minimum. Then we choose 7, then 12, then 15. And finally, we want to combine both subarrays of length 4. So then we'd always choose the starting value unless it's already been used. So then 2, 7, then 10, then 12, then 15, then 20, then 30, then 50. And that'd be the entire array. Yeah, in the code, you'd still need to check it. Don't have the answer. But yeah, in place implement or an in place iteration, you need to check them, even if they're already in order. Okay. So with heap sort, the general idea of it is that you want to continuously return the min or max and slowly update the array, moving from left to right or right to left, depending on which one you're doing. So in this example, if you wanted to sort these the array from least to greatest. First, we need to like set up the heap. So we'd need a max heap if we wanted to. If we'd need a min heap if we wanted to. My bad. We needed a min heap if we want to go from our max heap. My bad. Okay, I just relax. Stefan, do you know where the recording can be reached? YouTube? Oh yeah, it'll be on YouTube. Okay, so in the case that we're going from least to greatest, we want to use a max heap because we'd always want to place the greatest value at the end and slowly work our way from right to left. So first we need to actually set up the heap. So if we were given, oh, my bad. Thank you. So if we were given the array 3, 2, 8, 1, 5, and we wanted to perform heap sort on it, we'd first need to construct the heap or construct the binary tree. And then perform up heap operations until the heap satisfied the property of that the parent key is always greater than the child key. So we'd begin by working on the smallest subtree or the one nearest the bomb. So we can see that since we want a max heap, I want to swap 5 and 2. Then we'd work our way up. There's no subtree on the right hand side. So then I want to heapify the top half of the binary search tree. So I'd want to choose the max, which is 8, and swap it with the root, which is 3. And once that's set up, we'll have a heap. When doing these swaps, you'd want to, in place, you'd always want to make sure that you swap the values as you go. So in this case, I swapped 2 and 5. So I'd want to swap 2 and 5. And I'd want to swap 3 and 8. So this would be the max heap array setup. And from there, I'd want to return the root value and replace it with the bottom-most rightmost child, which is 2. So 2 would move up. And I'd perform down heap operations until it's a heap. I'd also want to, when I return the value from the heap, I'd want to place it at the right-hand side. So when I return it, it would look like this, with the ordered side being on the right-hand side and the unordered side being on the left-hand side. So I need to heapify again. So I need to look for the max. In this case, it's 5. Move it up. Make sure to swap it in place version. And then since it's a heap again, I can return. and take the bottom rightmost child and place it in the root. Five, 8. So this is what the heap would look like after I return the value. And then I would need to heapify to make sure that it remains a max heap. So again, simple swap the max with the 1. And it's a heap again. Make sure to do this in place implementation. And then we can return the value again. Return 3. And take the bottom rightmost child. In this case, even though it's in order, we still need to heapify because we still want to use a max heap. So we need to swap to one. Even though the array is already in order, we still need to check everything just to make sure that the entire array is in order and perform it as though the heap sort algorithm would, even though we can visually see that's already in order. So from there, I'll return 2 this time. And then move the bottom rightmost child, which is 1. And then I'll return 1. And it'll be in order. And that's heap sort. Are there any questions regarding heap sort? Okay, Stefan, is there a fast way to clear the screen? Yep. Okay. Thanks. So moving on, we have quick sort or pivot sort. So the point of this algorithm is that you want to choose a pivot located anywhere in the array. It depends on the code given in the question. In one of the assignments, the pivot was always the rightmost value. Sometimes people choose the middle value or the median of the 3, left, middle, and right. It depends on the code given. But in this case, we will always assume that the pivot's on the right-hand side. So when we perform quicksort, we always want to choose a pivot and then order the values or partition the values around the pivot. So in this case, when we chose 70, we want to break this array down into 2 arrays, one greater than 70 and one less than 70. So in this case, we go through the array 1 by 1 and slowly break it down. $90. 30. 30. 40. Okay. A thing to note when choosing a pivot is that when you choose a pivot, you'd always need to move it to the right-hand side. In this case, I'm choosing the right-hand element of the array. So because I'm choosing the right-hand element of the array, I wouldn't need to actually swap it. But if I was choosing a pivot in the middle, I need to swap the value on the right-hand side with the pivot. This is just for in-place implementation though. So then again, we partition them. So we choose a pivot, right-hand side, we choose 50, break it down into subarrays, and so on. So this would be 10, 30, 40. This would be an empty array. And we keep on doing that until we partition it down to element lengths of 1. Once we've done that, we want to combine all the subarrays that we have, or not combine them, but we want to, we want to combine the subarrays into what we had. Based on the pivots we chose. From left to right. In an in-place implementation, we'd swap the position of the pivot always to the right-hand side. But after we're done partitioning them, we'd always swap it back to where the left-hand pointer and the right-hand pointer intersect. Does that make sense? Okay, so are there any questions regarding quicksort? Okay, so moving on is bucket sort. So bucket sort requires a key and value when sorting the array. So we need to choose, we'd be ordering the key values in this case, and we choose n number of buckets, which is given to us when we perform bucket sort, and n representing the maximum key value. So in this case, we have the value of 7, which is the decimal number. So because it's a decimal number, we want to choose 10 buckets. So 0, 1, 2, 3. Then from there, we place the values. Oh, my bad. Wait, okay. I made a mistake. Okay, so the reason why we had 9 buckets was not because it was decimal, but it was because the key range we were given was 0 to 9. But later, we will in Radix sort, we'll use bucket sort, and the number of buckets will be determined by the basic number. So for bucket sort specifically, the key value or the number of buckets you have will be given to you in the value of n. Usually bucket sort is called by a sequence followed by the maximum key value or the range of the key values. So from there, you'd be able to determine the number of buckets you require, as well as the sequence of keys and the way you're going to insert them. So first, you'd iterate through, or once you initialized all the buckets, you'd assign you'd create a list at each bucket. And add it to it. So in this case, 7D would go to the bucket of 7 and be added to it. the value of 1 would go to the bucket of 1 and be added to it. 3 would go to 3 and be added to it. And if there's already a value there, since it's a list, we'd be able to add it on to the previous value. Once we have all the buckets, or once we've iterated through the sequence of keys, we then combine all the buckets in order from least to greatest key. So we'd combine 1 with 3, and then 3 with 7. And it'd be in order in terms of key value, not in terms of the actual value stored in the key value pair. Are there any questions regarding bucket sort? So an extension of the bucket sort is Radix sort. So bucket sort will use, or in this case, Radix sort will use the base value number of buckets. So if we were working in binary, we'd only use 2 buckets. If we were working in decimal, we'd only use 10 buckets. So when calling Radix sort, or at least in the assignment, we would pass the sequence, we'd pass the numbers as tuples. We'd pass the range of the key, or the base of the value of the tuples. And we'd also pass the current digit we're iterating through when we call Radix sort. And we'd iterate through it the number of times. We'd iterate through it. How much was it? The maximum number of digits of the largest number. So in this case, we have the largest number of 746. So 746 has 3 digits. So we'd use bucket sort 3 times. That makes sense. With I changing from 0 to 1 to 2 each time. So with the Radix sort, if I wanted to run through this example, first we'd order the least significant bit, which would be the first bit, or the first digit. And order them from left to right. So first we place them in their buckets. So we know that there are 9 buckets because we're working with a decimal, or 10 buckets because we're working with a decimal number. And we place them in the bucket according to which digit it is. So if it's 214, we'd see that the least significant bit's 4. So we'd add it to the tuple. We see that 324 has also a 4. 515 has a digit of 5 in its least significant position. 746 is a 6. Okay, messy. And 246 also has a 6. So from here, we're going to again combine all the buckets in the order we were given, or in the order we placed them in. So we begin with 214. Then 324. Then 515. Then 746. Then 246. So this would be the first iteration, and we need to iterate through it 6 times. So if you want to do it again, 1, 2, 1, 4, 4. So we'd look at the middle digit this time and place them all into the buckets accordingly. So we go through the array. We go through the sequence again. So 214 belongs in the 1 bucket. 324 belongs in the 2 bucket. 515 in the 5 bucket, or my bad, 1 bucket. Since we're working in the middle digit. Then 746 belongs in the 4 bucket. Then 246 also in the 4 bucket. Okay. So again, we go through all the buckets, collecting each of the terms. So 214, 515, 324, 246, and 746. Again, since each of these values have 3 digits, or the maximum value has 3 digits, we need to iterate through bucket sort 3 times. So we need to check the final digit. So again, we need the buckets. So I'll play the buckets. And we'd iterate through it one more time, and from there it'd be sorted. So 214 belongs in 2 bucket. 515, 5 bucket. 324, 3 bucket. 246, 2 bucket. 746, 7 bucket. Then I'd combine them in the order I added them. So 214, 246, 324, 515, and 746. And those are all the tuples in order. And that's Radix sort. Are there any questions? Okay.
What would be the advantage of using that over like just another sorting algorithm?
Radix sort?
Yeah, I mean,
Um,
separating the digits.
I know that
Could just
buckets.
be-
I know that bucket sort is a stable sorting algorithm. I didn't look into it too much, but I just know that it's special because of that, because it's able to use it's able to use something like called a comparator. But yeah, it does have its advantages, but for the sake of the exam, I just know it.
That's pretty cool.
Okay, so moving on, we have hash tables. So just an overview with hash tables. They store or they're able to determine the indices of values based, or the indices of values based on the actual value. And that's determined using the hash function. And the hash function depends on which type of probing we're using. So, or the hash function is given in the question. And in order to reduce collisions, aka values having the same key, we want to store, or we want to have some prevention measure in order to prevent collisions from occurring. Basically, having the same key. Okay, so first we have linear probing. So with linear probing, if a collision is to occur, we simply increment the key by 1 until we have an available spot. Do you guys want me to do this example? Okay. So this is linear probing. So we see that the hash function is hk plus j mod 13. Usually it's the table size. So in this case, mod 13. So in the case of an empty hash table, we'd simply do 13 mod 13, which would be 0. 13 mod 15, that's 2. 5 mod 13, 5. 28 mod 13, 2. So in this case, we have a collision. It's originally supposed to go in the position 2, but I need to move up by 1. So we want to increment j by 1 and put in the 3's position. And then we move on to the next value. So we have 1, 1's free. 14, 1 is not free. So 14 would originally go here. We'd want to increment until we have a spot available for 14, which would be at position 4. And then finally 2, where there's again another collision. So we want to increment linearly because we're using linear probing and place it in the position 6. Are there any questions regarding linear probing? Okay, so with quadratic probing, instead of incrementing, well, you'll still be incrementing I or j linearly. It's just that in the hash function, j is squared. So when when a collision will occur, instead of iterating by 1, 2, and 3, you'll go by 1, 4, and 9, because you'll be squaring the value of j. So if I want to do this example, again, empty hash table, no collisions will occur. So 13 mod 13, 0, 2. And then 5 mod 13 is 5. 28 mod 13, that's 2. So a collision has occurred. And then j is equal to 0 initially. And we'd increment it by 1. But we see that it's squared. So we're using quadratic probing. So we take 1 squared, which is 1. And we can see that's free. Then we check the value 1. 1 is free. 14 mod 13, that's 1. So a collision occurs. So we'd increment j by 1. And we'd square root it when we add it to the key. Or we not square root it, my bad. We'd square it when we add it to the key. And we see that another collision occurs. So we need to increment it again. So we do j is equal to 2. And when we add it to the key, we'd add 4 instead. So the original key was 1. So we'd want to add 4. So 1, 2, 3, 4. So again, another collision occurs. We need to increment j again and square it when we add it to the key. So that'd be 9. So 5, 6, 7, 8, 9. And it's an open spot. So moving on from there, the final value is 2. Collision occurs. So we increment by 1. Then we increment by 4. And we have an open spot. And that's quadratic program. Are there any questions regarding quadratic program? Okay, moving on. So double hashing occurs when we don't use either linear probing or quadratic probing, but we instead use a secondary hash function and we increment it linearly. So the hash function will change depending on which key you put in and when a collision occurs. So I'll just show you an example. So 18 again mod 13 would be 5. 41 mod 13. So that's 2. 22 mod 13, that's 9. 44 mod 13, that's 5. Okay. So we'd see that a collision occurs. And we need to use the secondary hash function. So we see that the secondary hash function is 7 minus k mod 7. So in this case, the k would be our key, which is 5. So 5. Or no, it'd be the value 44, not the key. Mod 7. So 44 mod 7 would be 2. So our secondary hash function would be 5. So we'd increment j by 1 when a collision occurs. So j would be 1. And then the value of our current key, or the value of the new key would be the value of our current key plus 1 times our secondary hash function, which is 10. And we see that 10 is free. So I meant to put 44, my bad. So from there, we would insert the value of 59. So 59 mod 13 is 52. So 7. Yeah. So it'd be 7. There's no collision. The value of 32, 6. 31 would be 5. So a collision would occur. So we need to resort to the secondary hash function, which is dk. So 7 minus 31 mod 7. So 31 mod 7 is 3. And that would be equal to 4. So when a collision occurs, we increment it by j by 1. And we determine the new value of the key by multiplying j and the secondary hash function with the original key. The original key is 5 plus 1 times 4, which is 9. Another collision occurs. And this time we just increment j by 1. You don't need to do any more math. And 31 will go in the spot of 0. Then finally, with the value of 73, so 73 mod 13 is 8, 8, and the value of 8 is open. And that's secondary or double hash.
How do you know when to stop looking for a spot?
Oh, what do you mean?
If you keep incrementing,
If you keep like colliding?
yeah,
So with so with a hash table, you usually want to do this n number of times, but there are some times in which so there's the thing called the load factor, and generally speaking, when a load factor is too high, like 0.8 or something, like, so this is just the number of elements in the array divided by the total size there. So if that value gets too high,
yeah.
then they'll just stop accepting values.
Okay.
Yeah, or they'll increase the size of the hash table.
Okay.
Yeah.
It's like you could also know, like, if you end up with a pattern of the same values, I don't know if that's possible. Like you keep having the same, trying to put it in the same
Yeah.
pattern, and then you can detect that.
With linear probing, that'd be an issue because values would end up like clustering around where there's a collision. That one way to avoid that was with quadratic probing.
Yeah.
So the other way to avoid that was with double hashing, because double hashing, the secondary key would be like random, basically for each value. So
Okay.
versus with, and like with quadratic probing, it wouldn't increment linearly, so values wouldn't like cluster in one spot and cause a lot of collisions.
Yeah.
Okay.
So it's random for double hashing. Like, it would be a
Yeah,
pattern.
yeah, it's basically random. Okay. And that's it for hash tables. There was also removal. Just make sure that when removing a value, you determine its key, find it, and then remove it. And when you remove it, you make sure you write available, so that when you attempt to search for another value, you won't run into any errors. Are there any questions regarding hash tables? Okay, so moving on to graph traversal. So, okay, I know this looks like a lot, but there's like 4 ways you can represent a graph, and this one isn't too commonly used, but these were all presented throughout the course. So an edge list basically connects an edge to the vertex or like save the addresses of the vertexes it's connected to, or vertices it's connected to. So in this case, you can see that L1 is connected to the vertex V1, V2. And it's the same in the diagram. And the addresses would be stored in an order such that it's directed. So the first address stored would be the address or the node it's pointing away from, in this case V2. Hence why it's on the left-hand side. And the second address stored would be V1. So the node is pointing towards. This represents like an ordered pair. Since the vector in this case is directed. So moving on from edge lists, there's also the adjacency lists. So for each vertex, we can just store the directed pair as a list. And this is usually common in assignments and tests. So yeah, and the order of the pair does matter as it indicates where it's going from and to. But all of the ordered pairs, first values would be stored under the ones list because they're all attached to one node. And then with the adjacency matrix, so the row number and the column number will represent the nodes it's going to and from. So the row number will represent the place it's going from. Row number. And the column number will represent the place it's going to. Row number, column number. So if I wanted to check for a directed vector, I could check the vertex it's going from. So in this case, if I wanted to check where this was located in the matrix, I'd check the one vertex. And then since it's going from one, and then I check the 4 vertex, that's where it's going to, and I check where they intersect. And the value will be 1 if there is a connection between the two nodes, and 0 if there's not. In an incidence matrix, there is the value of -1 to indicate whether or not the vector is pointing to or away from the node. And the rows this time represent edges, not vertices. Or my bad, the columns represent edges, not vertices. Where -1 represents pointing toward the row number. So if I wanted to check, for example, V1 to V2, it's pointing toward itself. So I check V1 and then see that it's -1. Are there any questions regarding any of the graph representations? Okay. These are all the time complexities. I don't recommend memorizing them. But the space ones are pretty obvious to memorize since they store it depending on what's stored, whether it's edges or vertices, you know the space complexity. But in terms of inserting vertices or inserting edges, I wouldn't really recommend memorizing. Are there any questions regarding time complexities? Okay, so moving on, we have BFS and DFS. So the point of BFS and DFS is to search through every node of a graph once. However, BFS and DFS operate differently in that the order in which they visit nodes is different. So for BFS, we're given for BFS and DFS, we'll always be given a starting node. So in this case, in both cases, they're A. And if I wanted to, if I wanted to do the BFS algorithm, I need a queue. So let's set up an empty queue. And then I'd add the value that I'm currently at. And then I would check for any neighbors at the value I'm currently at. And then if I spot any neighbors, I'll add them to the queue. Okay, so once I'm done that, I'll mark it as checked and remove it from the queue. So then it's checked. So then now I can check the value, or I'll dequeue a value. So in this case, it'd be B, and check its neighbors. So it has nothing. So I dequeue it and mark it as checked. And then I dequeue the value of C. Or no, first I check its neighbors. I see that it has neighbors. I'd enqueue those neighbors. Then I'd dequeue it, mark it as checked, and then dequeue the next value, which would be D. I check to see if D has neighbors, which haven't already been added. F's already been added, so it has no neighbors to be checked. So I dequeue it, mark it as checked. Then I dequeue the next value, see that's E. See if it has neighbors, no neighbors. DQ it, mark it as checked. DQ from the queue. See if the value F. See it has no neighbors, mark it as checked. So the order in which I mark them as checked would be A, B, C, D, E, F. But it'd be different if I did a BFS algorithm. So with a BFS algorithm, the general idea is that you want to keep investigating nodes further until they have no more neighbors. Versus with breadth first search, you search all adjacent neighbors first before searching for them. So if I wanted to start with the value A, I'd check to see if A had any neighbors. Oh, wait, my bad. First, I'm supposed to instantiate a stack. So DFS uses a stack while BFS uses a queue. So first I want to create a stack. Next, I want to push the starting node, which is A. And then check to see if it has any neighbors. So when determining which neighbor you want to go to first, you generally want to do it in alphabetical order. However, this depends on the code written. But generally speaking, you want to do it in alphabetical order. It looks as though it didn't do it in alphabetical order because it started with D. So I'm assuming it does it in reverse alphabetical order. So in this case, I'd check the value D, and then I check to see if D has any neighbors, in which case it does. That's the value of F. Then I check to see if F has any neighbors, and it does. It has the value C. So I add it to the stack. And then I check to see if C has any neighbors, and it does. Or any neighbors that have not been checked yet, and it does, and D. So I added the stack. And then I check to see if E has any neighbors. It doesn't. So then I remove from the stack and then go back to the previous value I was at before, which was C. So I check to see if C has any more neighbors. There are no more neighbors that aren't checked. So remove C from the queue, go to F. Check to see if there are any neighbors at F that I haven't checked already. And then I see that there are none. So I DQ it, go to D. Check to see if D has any more neighbors. D doesn't have any more neighbors. Remove it from the stack. Check to see if A has any more neighbors. It does. So I add it to the stack. Check to see if B has any neighbors. It doesn't. Check to see if A has any more neighbors. It doesn't. The stack's empty. It's done. And the order, again, I traversed in was the following. Well, those questions. Yeah, F and C are neighbors. I'm not quite sure why the line's dashed, but yeah, just assume they're neighbors. Are there any questions regarding BFS and DFS? Yeah, the order can differ based on the like neighbor you choose in DFS. So if I chose to go alphabetical order, I would have hit B at the very beginning. So if I wanted to do it in alphabetical order, it'd be A, B, there's no neighbors to B, and the order would actually matter. I don't know if you want me to complete it, but it just shows that the order actually does matter if depending on which neighbor you want to choose. It also applies to BFS too, in that if I wanted to choose D first as an adjacent neighbor, then it'd be A, B, C, or A, D, C, D, or A, my bad, A, C, D. It depends on whether or not, or like the order in which you choose your neighbor. They'll usually tell you. Does that make sense? Are there any more questions? Okay. Okay, there's actually one more question. Okay. So given that an algorithm produced the following order, which of the following algorithms were probably, or which of the following algorithms were used, basically? So, okay, given the context of the question is it's between BFS and DFS. So it's starting at root node, it's starting at value 5. So if I wanted to check between BFS and DFS, I could see that the next set of values is 3 and 7. And I know that DFS would not go back to check on 7 after checking on 3, or the other way around. It would not go back to check on 7 if it, or not go back to check on 3 if it already checked on 7. So because of this, I know that it's breadth first search. Unless it was none of the above are correct, because the order was originally wrong. So it's between D or E. So I'll check the breadth first search. So you begin at root node 5. Then you check for any adjacent neighbors, 3 and 7. Add them to the queue. Mark 5 is checked. Check 3. C3 has neighbors, 2 and 4. Add them to the queue. And at this point, I already know that it's BFS. I could complete it, but all the nodes are already checked. There's no point. Does that make sense? Ignore all the blue pen. This is from another final. Are there any questions regarding BFS or DFS in general?
started at a node other than the root, how would that change the algorithm order?
It changed the order drastically. It would. Usually you do start at a node, root node. But again, you can always choose whatever node you want to start at. Because you're not just working with trees,
Yeah.
you're also working with graphs at times. Like these could be connected,
Yeah.
and you could still perform a BFS. It just depends on the order in which you visit your neighbors. So let's say I started at C.
Yeah.
It would matter, or like since this is since this is a directed edge, I wouldn't be able to visit C to A. So
Right.
I need to choose between E and F.
Okay.
And the order in which I choose them is based on what they tell you. Usually it's alphabetical order. So maybe like, since it's a breath first, you do C, E, F. And then, yeah, so I don't know. Do you want me to complete it?
Yeah.
Oh, okay. Okay, sure. Then, so add it to the queue. Then I know that C is checked. Then I check E. Let's assume that the blue line's there. So I check E and I see that it has a neighbor, E. Add it to the queue. Add it to my traversal. Then
Assuming would be that back arrow. Or,
which backer? The one I drew?
yeah.
Yeah. Assuming it's there, yeah. Okay. Then
But if that wasn't it, it would just be CF and then you're done. Like, you
C,
wouldn't be able to go through the full.
you'd go through the BFS and DFS will go through the entire tree as long as the trees are like, not the tree. It'll go through the entire graph as long as it's connected, like guaranteed.
Okay.
So
So how do we get?
let's assume that, okay, let's assume that that arrow's not there. Do you want me to do it now?
Yeah.
Okay. So then, so CEF, we have the QCEF. So we already checked C. We check E, we see that there's nothing there. Then we check F. Now we see that F, oh, you're right. Well, it's a directed edge. Yeah, you're right.
So, okay.
'Cause it's a
So we would
subtree.
add it there. Yeah.
I didn't see that, my bad. Yeah, you're right.
Okay.
But usually they only give like undirected edges, but
Yeah.
yeah, okay. Yeah, but you're right though. Okay. Are there any more questions regarding BFS or DFS? Okay. So moving on to Dijkstra's algorithm. So this is used to determine the shortest distance possible from one node. So when forming this algorithm, you want to create an array based on the number of nodes there are. So in this case, there are 9, 8, wait, 1, 2, 3. There are 10, my bad. There are 10 nodes. So you'd begin by creating an array of length 10, which with each node representing a value in the array. Okay, so since we're starting at the value of A's distance from A will be 0, and we'd want to initialize the array such that we're only considering directed edges to A and no other possibilities. So we'd only consider A to B, A to C, A to E, and A to D. So we'd set those values initially, but we'll change them later on. So for the remainder of the values, you set them to the largest possible integer that you have. So in this case, we use infinity. this basically shows that it's unreachable currently, but as we progress through the algorithm, we'll eventually find its shortest value. So I don't know if I said this, but Dijkstra's algorithm is a greedy algorithm. So every opportunity you have to minimize the path, you will take it. So what I mean by that is with the distance, for example, for value 3, if I wanted to, or not 3, or for example, for the distance for value j, initially it's infinity, but eventually as I progress through this algorithm, I will find a better path and replace it with that path.
Why does B have 10 next to it?
You can get to it.
The actual node B has the number 10 next to it, shouldn't it be 13? Oh, never mind, sorry.
Wait, is it? Wait,
I figured it out.
is it really? I2. I don't see it initially, but I'll probably see it afterwards. This was from the answer key from the assignment, but I'm pretty sure it's 10.
That's it.
Wait, yeah.
What are the numbers by the nodes again?
They represent the weights of each path. So like, if you wanted to get from A to C directly, it'd be 6. It costs you 6.
Okay, and then between that, like the weight, the number on the edges.
Like the orange numbers represents the weights. The purple numbers are the answers. Yeah.
Oh, right. So the 10 is like, because we're starting at A. So initially it's 13, but then we found a short distance.
Yeah. The highlighted blue represents a spanning tree of the minimum, like not the minimum spanning tree, but the shortest distance spanning tree. So basically a spanning tree is like a tree which contains all the, like contains no cycles and contains all the nodes of a graph. So it is a spanning tree, but not a minimum one. I'll talk about it afterwards, but basically you'd only follow the blue highlighted path. You never use the like unhighlighted path ever. Okay, so back to the algorithm. So initially, these are the values initialized. So with Dijkstra's algorithm, I want to choose the shortest path currently in the array and check its neighbors. So first, I'll check the value, or I'll check the node E because it has a distance of 3. So we already assume that A is checked. So we won't ever repeat checking A ever again. So now we'll check the value of E and all its adjacent neighbors. The order in which we check them doesn't matter because we'll check them all afterwards. So we can go from E to C, but we see that the value going from A to E and E to C is 7. But 7 is greater than 6. So we don't swap the values. We see that I is currently infinity and 5 is less than infinity. So we swap it out with infinity. Okay. So next, we check the value for D, and we see that A to E and E to D will result in 11. 11 is greater than 10, so we don't take it. So we checked all the neighbors of E. Oh wait, no, I missed J. My bad. So J is infinity. J 3 plus 3 is 6. So we replace 6 with infinity. Okay, so next we again go through the array. We see which values we haven't checked already, and we take the smallest possible value and check that node. So in this case, we check the value I. because it has the smallest value that we haven't already checked, which is 5. So if I want to check the value of 5, I'm going to need to check all its neighbors now. So f is currently at infinity. And the value to get to I is currently 5. So 5 plus 4 is 9. So I update infinity to, I go from infinity to 9. I check to see the distance from j. And I see that it's 5 plus 5, so which is 10, and it's not less than 6, or not greater than 6. So then I move on. D, 5 plus 6, it's 9. Wait, no, 5 plus 6 is 11. 5 plus 6 is 11. 11 is greater than 10, so you don't take it. So then you keep moving on. Check again. The smallest value in the array of the value of the nodes that haven't been checked. So that's 6. Oh, wait, no, first you do C. Okay, so the order in which you check them is arbitrary, but usually they want you to check them in alphabetical order, because occasionally they'll ask you for the edges visited, and that would matter. Okay. So moving on, we have J. So then we check the adjacent neighbors of J, which is F, G, and I. We already branched to J from I, so we don't need to check it. Okay, so we check from J to F. We see that the distance is 7. So 9 is less than 7, or 7 is less than 9, method, and then replace it. Then we see that the distance to G is infinity, and then we see that we can replace it with 7, so we do. And we check the distance to I. 6 plus 5 is 11. I is currently 5. We don't replace it. We go to H, or no, we check for the smallest value, which is J. Oh, whoops, I already did J. Okay, again, arbitrary values. I should have checked C first, but so I should have checked C for its neighbors. So the distance from C to its neighbors is 14. 6. 10 and 11. 15. So A is already 0, so we ignore it. B is 14, B is already 13, we ignore it. E is 3, we ignore it. I is 11, so we ignore it because it's already 5. And F is 7, and we ignore it because we don't want to take 15. So C connects to none of the values. So that line. Should have been drawing these. Okay. So now that we already checked C and we checked J, we look through the array again, and we see that our lowest value is 7. So we check the neighbors of 7. 7 plus 3 is 10. It's 13, so it's the shorter path. We replace it. We check from F to H. It's 11. It's not shorter than 8. Oh no, currently it's infinity, so we actually take it. I'm making so much math, but math mistakes, but 7 plus 3 is 10. So we take it because it was originally infinity. Then we check G. The distance from F to G is 5, or A to G is 15. So it's currently 7. We don't take it. The distance from F to J, or F to J, will be 8. So we don't take it. Then Stefan. Oh, sorry. Do you mind if I take a quick break? I know I'm in the middle of a Dutch search, but I just need to take a quick break. I think my nose is bleeding. Oh, okay. Sorry. I'll be right back. Sorry, I'll be right back. Hello, sorry, I'm back. Yeah. Okay. Sorry about that. I left mid Dijkstra search. So yeah, I believe I was searching F. And I would check all the adjacent neighbors. So I'll check F to C, but I would see that F to C would result in 16. That's greater than 6. So I wouldn't replace it. And finally, I do F to I, and F to I would be for 11, which wouldn't be greater, or would be greater than 5. So we wouldn't replace it. So again, we go through all the nodes. We check G. So we check G, and we check all the adjacent neighbors of G. So we check from G to H. We see that G to H gives us 8, and it's currently 10. So we replace it. And we remove the previous path. Next, we check G to F. So G to F would be 15. And 15 is not less than 7, so we don't replace it. And then finally, we do J to G, which was the path in which we came. So we don't check it. But in code, we do. So it would be 7. So we wouldn't replace it because it's 6 currently. No, it'd be 8. Yeah, so we don't replace it. Regardless, we don't replace it. But moving on from that, we then check the next node. We then check the smallest node, which would be H. So we check all the neighbors of H, which would be B, F, and G. We see H to B is 11, which is not less than 10. We see that H to F would be 11, not less than 7. We see that H to G would be 9, which is not less than 7. So we don't change it. So from there, we have H checked. Next, we check B. So we check B and all its neighbors. So we check from B to A. So that'd be 23. Okay, it's not less than 0. We check B to C, which is 18. We don't take it because it's not less than 6. We check B to F. B to F, 13, not less than 7. We check B to H. B to H is 13 currently, which is not less than 8. So we don't take any of the neighbors. Next, we check D. We check D. and it's all its neighbors. So we go from D to A. So its current value is 10 plus 10 to get to A. That's 20. We don't change it. We go from D to I. D to I is 16 and I is currently 5. We don't replace it. We check D to E. D to E is 18. We don't replace it because E is 7. And that would be all the nodes checked. So those would be all the shortest distances from A to J. Are there any questions regarding texture search? There's a question following regarding vertices and edges visited. But I'll get to that in a moment. But are there any questions regarding how I did the extra search? I know it took a while. Sorry about that.
The order which we go through the vertices is based on the closest, the shortest distance.
Yeah, shortest distance to A. And you got to make sure it's not checked already.
Okay.
Okay. Okay. For vertice order, so with the vertice order, you would you would write down the order in which, or you write down the order going from smallest to greatest. So in this case, we see that A is the smallest. Then we see that E is the next smallest. And then we do this so on. So it'd be I, then it'd be C, then it'd be J, then it'd be F, G, H, then it'd be B and D. For the edges in order, we follow these nodes connected to like in the spanning tree. So it'd be A to C, A to D, A to C, A to E, and A to D. And A to E. Then it would be next vertice at visit is E. So I'd visit E, and then I check all adjacent neighbors. So it'd be I and J. Then it'd be I, which would have nothing connected to it. Then it'd be C. C has nothing connected to it. Then I'll check J. J has F and G. Next, I check F. F has B connected to it. Then I'd check G. G has H connected to it. Then I would check H. H has nothing connected to it. Then I'd check B. B has nothing connected. No, that's a, my bad. That's a mistake. Then I check D. D has nothing connected to it that we already haven't traced. And again, this is the order of the vertices. And the distances would be this array. Is that okay? Are there any questions regarding edges visited or vertices visited? This is just for this exam. Okay. Moving on to Prim's algorithm. So with Prim's algorithm, we want to find the minimum spanning tree. So minimum spanning tree being the tree with the lowest total weight. So the it would be different from the Dijkstra's spanning tree in that it wouldn't be the shortest distance from the root node. Instead, it would be the minimum total weight that we would need. The minimum total weight of a spanning tree given a root node. So to actually create or to actually use Prim's algorithm, we need a starting node. So we choose the node A. And then from there, we'd always choose the lowest edge weight and connect the node attached to it. And then from there, we'd always choose the lowest edge weight and add the edge to the spanning tree. And we'd stop once we drawn n-1 edges. And we'd always look out for no loops. So from here, I would begin by circling all my options. And then go from there. So I originally chose 3, but now I have the option of choosing 2. So I choose 2. And then I'll circle more of my options. And then I would choose the lowest value option, which would be another 3. So again, I'd begin by circling my options. And then I choose the lowest value option, which is 1. I would again begin by circling my options. Choose the lowest value 1, it's 1. Extend, add the node, circle my options. Then choose the lowest value 1. Add the edge, circle my options. So then I choose 3. In this case, I have multiple options because I can choose the 3 here, I can choose the 3 here, or I can choose the 3 here. But I need to ensure that I don't form any loops. So I can't actually choose any of these because this would form a loop. This would form a loop like so. And choosing the other one would form a loop like so. So because of that, I can't choose either of them. So I need to avoid choosing 3s at this point and look for any 4s. So I begin by looking for some 4s. And I see that there's one here. So I add that edge, and add that node. Circle more of my options now. Okay, then this one out. Then I see that there's another 4. If I wanted to choose it, I'd form another loop, but this one would form, I'd form a loop like so, which is not allowed in the spanning tree. So I can't choose that 4. So I need to look for a 5. So I could choose this 5, but again, it'd form a loop. So I choose another 5, which would be this one. Again, a loop, I can't choose it. So I move on to 6. 6, I see there's a 6 here. This one wouldn't form a loop, and I'd add the node D. And at this point, I'd have all the nodes circled, so that'd be the minimum spanning tree. And I know that's really messy, so let me clean up. deleted this edge. Okay, and I believe that's the minimum spanning tree. So a regular spanning tree is any tree which doesn't have any cycles and contains all the nodes of a graph. So this is a spanning tree because it contains all the nodes of a graph, all the nodes of the graph, but it doesn't have the minimum total weight that this spanning tree does. Because the total weight of this spanning tree, I believe it was like 22 or 26. But yeah, if you add all the values like of all the edges, you'll find that this value is like lower than the spanning tree of this value, or the total value of this spanning tree of it. For if you're asked to make a regular spanning tree, then yeah, you can choose any edges so long as there are no cycles. And you get all the nodes. Okay. I don't think I'm going to go over another dexterous. Yeah. Is everything okay with the Prim's algorithm though? Are there any questions regarding the Prim's algorithm? Okay, moving on to Kruskal's algorithm. So in this spanning tree, we aren't giving a starting node. So instead, what we will do is we will always just choose the the shortest value edge. So we'll begin by choosing the 1. We can choose either, but we will always choose this shortest value edge so long as it doesn't create any cycles. So I'll choose randomly. I'll choose F to J. So since it's 1, I chose F to J, and now I will have F and J as nodes in the spanning tree. So then I'll choose 1 again, because there's another 1, and it doesn't form a cycle. And then I'll add G to the spanning tree. Now I see another 1. It's conveniently connected to the G node, but it doesn't have to be. So I'll connect it to the spanning tree. So then I look for another edge. So there are no more 1s. So I look for 2s. I see a 2, so I take it. So then I look for any more 2s. There are no more 2s. So I look for 3s. I see some 3s. I see a 3 here, 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 and here. So usually I did say you could choose arbitrarily, but you would usually want to choose in alphabetical order. So given the edges and the nodes are connected to, you'd usually want to choose B to F because it's connected to the node B. But again, you could choose it arbitrarily. You could choose this one, but it's not in the green highlight. But this is also another option for a minimum spanning tree. So either of these would work, but not both, because that would be a loop. So for the sake of the green highlight, I'll choose the 3 from B to F. And then I'll choose the 3 from E to J because there's no loops that are formed. And then I see another 3 from A to E. I'll take that edge as well. And then I think that's all 3's done. So yeah, then you'll move on to the edges of 4. So from 4, again, we know that creates a loop from like so, even though it doesn't look like it, that forms a loop. So we don't want to take that edge. So we don't take I to F. But we can take E to C because no loops are formed. And then we check to see if there are any more fours. There are no more fours. So we check for fives. I see a 5 there. And I see a 5 here. Both of these will cause loops. Let me use red. This one will cause a loop like that. And this one will cause a loop like that. So from there, I'll choose from the 6 edges. So 6 edges. So I could choose this one, but again, it'd form a loop. So I don't choose it. And then I choose this edge. And that'd be all the node circle. Are there any questions regarding Kruskal's algorithm? Okay, that's done. So, are there any questions just generally about anything from the content covered or not covered? Prim's algorithm, sure. Okay. Okay. Okay, so with Prim's algorithm, you're given a starting node, and in this case, it's A. So with A, when you're given a starting node, you always want to choose the shortest edge, which is connected to your current. What's the difference between the two? Okay, so with Kruskal's algorithm, you are not given a starting node. You will always choose the shortest edge, so long as it doesn't produce any cycles. But with Prim's algorithm, you are given a starting node, and you have to always make sure it's connected to the minimum spanning tree. So in this case, I have to start from A, but in Kruskal's algorithm, I have to start, or not I have to start, but I would want to start from, or I'm not really starting anywhere. My bad. Like I'll always choose an edge anywhere. Does that make sense between the difference? Between the two? Difference between the two? Okay, and with I'll go over Prim's algorithm. Okay, so with Prim's algorithm, I'll start with node A, and I'll choose the shortest edge that is connected to the node A, or my like options. So I'll start off with these options, and I'll choose the smallest value. So I'll choose A to E. And this will expand the options I can choose from. So I can now choose from these options, and I'll always choose the smallest value. I just need to make sure that no cycles form. So in this case, I can go from E to J, and there are no cycles will form. Oh, I was supposed to go from E to I. Okay, that's my vote. Because I had 2. So I'll go from E to I first, because it was 2, less than 3. Then I'll go to 3. Then I'll go to F. Then I'll go to G. Then I'll go to H. Now here I can choose these three values, but this one will cause a cycle. So I can't choose it. I'm sorry, it's messy, but it'll cause a cycle. So I can't choose it. But so that's off the table. So I can choose this one. It won't form a cycle. It's an alternative minimum spanning tree. But again, the green highlight goes in the other direction. So I'm just gonna choose that one just for clarity. But again, you could also go from B to H. It's just that you couldn't choose the value from B to F. So yeah, okay, so then I'll connect to B, and that's the three chosen. I can't choose this one. So then I will look for any more threes. There are no more threes. I look for fours. I see a 4 here, but this one will cause a cycle. So I'll choose this 4. This 4 won't cause a cycle. And then I'd look for any 5s. Oh, I was supposed to circle this one, but I look for any 5s. I can't choose that 5 because it'll cause a cycle. I can't choose this 5 either because it'll cause a cycle. Like this. So I move on to the 6s. And I can choose this 6, but it'll cause a cycle. So I don't. And that's the entire minimum spanning tree. Because all the nodes are now circled, or supposed to be. Okay. Are there any more questions just in general regarding CSI?
We go up to the ON or the big O rotation.
For which one?
The first question.
Oh, complexity?
Yeah.
Here. No, this
The one above.
the multiple choice. This one.
Yeah. So
What about?
found. So we want to find big O and big theta.
Yeah.
So
Oh, big O and big omega.
big omega. Okay.
Oh, well,
Big theta is-
it's both. Big theta is both of them.
okay. And so how do you?
Okay. So for the big O, do you agree with me that the big O is n log n?
Yes.
Okay. Okay. Do you agree with me that the
Okay.
big theta is n log n?
Oh, you mean omega?
No, theta.
Oh, I thought.
Oh wait, this is, oh my bad. Yeah, you're right. You're right. Yeah, this is omega. Yeah, I drew omega. You
Okay. So that's the lower bound.
yeah.
I'm not sure why. It's like
It's because there's no like,
there's no other way to do it faster, to run through the loop
yeah,
faster. Okay. And then
it's because
big omega is just like the minimum of that.
yeah,
Or the
it's the best case.
best case of the two. Okay.
Yes.
Okay. That's good.
Yeah. Okay. Are there any more questions regarding anything? What time is it? 5:50. Oh, it was 3 hours.
Oh, you're right.
Wha-
It's okay, we covered a lot.
Oh my God. I think that was everything. I recommend though, like, look, I brushed over Quicksort too quickly. I think it was pretty not great.
Yeah, go over and check that over.
Yeah. Because Quicksort uses pointers, and I didn't mention them a lot during the explanation. But
Okay, when you did like the traversal, what was this notation you had? Let's see.
Euler's walk, I think,
Okay,
or I just call it Euler's method.
so Euler's method for preorders like on the left.
Yeah.
And then I'll check it out. Okay.
This.
Thank you very much.
Are there any more questions just in general regarding CSI? On the virtual Zoom. Okay, sounds good. Okay, then I think I'm gonna stop sharing. Okay, thank you for coming. I'm gonna post them in the CSI server. I can also put in the link in the description. Yeah. Okay. All right.